Hello, my dear students. Welcome back to the session. Today we are going to discuss about the topic called resonance. Okay, so we are already in AC circuits. We discussed several problems in the previous session. Okay, or previous sessions, and we'll now move on to an important topic in any competitive exam point of view, whether it is GATE or any other competitive exam point of view. Okay, the resonance is very important here. Okay. So, what is resonance and where is it really useful? Okay. See, particularly the resonance is very important in communication systems. A signal transmitted by the transmission station, received by the receiver, is based on the resonance phenomenon. Okay, you have some transmission station, receiver. Okay, now transmission station will transmit a signal, and receiver will receive a signal. Understand, all of you? And all these are based on resonance phenomena. Understand, all of you? Okay. Now, what are the resonance circuits? We also call them as frequency selective circuits. We call resonance circuits as even frequency selective circuits. See, some circuits, if we take which consists of some RLC elements, some circuits which consist of RLC elements will give current output or voltage output or power output that is greater at some frequency or one frequency or some range of frequencies, small range of frequencies, than that at all other remaining frequencies. I repeat once again, there are certain circuits which consist of RLC elements which yield current output, voltage output or power output that is greater at one frequency or small range of frequencies, okay, than that at all other frequencies. Those particular circuits are called frequency selective circuits or resonance circuits. Understand, all of you? Okay. Well, how do you define resonance in electric circuits? You might have heard about resonance in your +2 level in a very important topic called sound. Yes or no? But when it comes to electric circuits, you define the resonance in a different manner. You can't really, take that definition what you heard about resonance in your +2 standard. But here we generally apply this resonance concept in circuits. See, you take any RLC circuit. If any one of the parameters is varied, okay, you take any RLC circuit and excited by the sinusoidal usually, okay, and vary any one of the parameters, whether it is resistor, inductor, capacitor or frequency, whatever, in such a way that if the phase difference between the applied voltage and applied current, I mean input voltage and input current phasors, is zero, then the circuit is said to be in resonance, or the circuit is said to be resonant. Understand, all of you? Okay. Or else the phase angle difference between current and voltage zero, it means that the input source, whatever you have, the voltage and current, the phase difference between these two is zero, is nothing but cos zero. That means power factor. Power factor is always question of angle difference between voltage phasor and current phasor. If the input power factor is unity, because cos 0 is 1, right? Unity, then also you can say the circuit is said to be resonant, or the circuit is said to be in resonance. See, when the power factor is 1 or phase difference between voltage and current 0, that means the circuit is behaving like what? Resistive. Yes or no? When the circuit is behaving like resistive, do you have any imaginary part in impedance? No. In admittance? No. Yes or no? Okay. Therefore, if the imaginary part of the input impedance is 0, or if the imaginary part of input admittance is 0, then also the circuit is said to be resonant or in resonance. Understand all of it? Okay. So, very, very important definition. Okay. So, let's note down one by one point. Okay. First point. Write down. First point. I dictate the point here. Write down. Write down the points here. The concept of resonance. The concept of resonance. The concept of resonance is very important. The concept of resonance is very, very important, or very important, especially in communication systems. Especially in communication systems. The concept of resonance is very important, especially in communication systems. Full stop. A signal transmitted by the transmission station and received by the receiver. A signal transmitted by the transmission station and received by the receiver is based on resonance phenomenon. Is based on resonance phenomenon. Okay, next point. Next point. Very, very important point. Some circuits which consist of RLC elements. Please write down. Some circuits which consist of RLC elements will yield. Some circuits which consist of RLC elements will yield current output, voltage output, or power output. Power output that is greater at one frequency, that is greater at one frequency in bracket or small range of frequencies or small range of frequencies than that at all other frequencies full stop, than that at all other frequencies, full stop. Such circuits are called frequency selective circuits, or such circuits are called frequency selective circuits or resonant circuits. Clear, all of you? Such circuits are called frequency selective circuits or resonant circuits. Definition. Third one, very, very important. Definition. How do you define resonance? Okay. In any RLC circuit, if any one of the parameters is varied, if any one of the parameters is varied such that, if any one of the parameters is varied such that, okay, so please put a colon here, such that, number one, the phase difference between input voltage phasor and current phasor is 0, or number 2, the power factor of the input source is unity. Okay, because phase difference 0 means power factor is unity, yes or no? Or the imaginary part of input impedance is 0. The imaginary part of input impedance is 0. Or obviously when imaginary part of input impedance is 0, then the imaginary part of input admittance is also 0. Yes or no? Input impedance is 0, or imaginary part of input admittance is 0. Okay. Then the circuit is said to be, resonant or in resonance. Understand all of you? Okay. So this is how you define resonance. There are 3 important points to be remembered all the time. Whenever you come across resonance, these are very, very important. Okay. Understand all of you? Okay. So how many resonance circuits are available? Broadly, you divide them into series and parallel. Okay. You divide them into what? Series and parallel. Broadly, you divide them into series and parallel. RLC series, RLC parallel, resonance you can take. Okay. So I hope you have noted down this, right? Okay. Well, based on the elements, based on okay, configuration of the network, configuration of network, we divide into RLC series resonance, RLC parallel resonance. Okay, please note down. Let's start with our discussion with series resonance, and then we'll move on to parallel resonance. Clear? First we take series resonance, then we'll move on to parallel resonance. Clear all of you? Well, the first one is RLC, series resonance. JXL minus JXC. So how did you define resonance? If any one of the parameters is varied, right? If any one of the parameters is varied in such a way that the phase difference between voltage phasor and current phasor is 0. Okay? Now this is A, this is B, let us say. The frequency of this particular source is, let us assume that F, that is in hertz, or else omega, that is in radians per second. Okay? So Z can be written as what? R plus J XL minus XC. For the circuit to be resonant, definitely imaginary part of impedance must be made 0 or become 0. Therefore, XL minus XC is equal to 0. Now here, assume that you are varying the frequency. Okay, in any RL circuit, if any one of the parameters is varied. Now here the variable I am taking what? Frequency. Okay, you can change either L or C or anything. It doesn't matter. Understand all of you? Okay, you can change L, you can change C, you can change R, you can change frequency, anything you can change. But in this context, I am changing the frequency. Understand? Okay. So what do you get here? The frequency at which, because I am changing the frequency, right? The frequency at which resonance occurs is called resonant frequency. So I call FR, okay, or omega R. Okay, these are resonant frequencies. Resonant frequency. So, okay, one is in hertz, the other is in radian per second. So now XL is equal to XC. Understand? Now you have omega RL is equal to 1 by omega RC. From this you can understand omega R is equal to 1 by root LC. Yes or no? From this you understand FR is equal to 1 by 2 pi root LC. Clear? So this is in hertz and this is in radian per second. Clear? You also know that this is VR, this is VL, and this is what? VC. Yes or no? You also know that the phasor diagram, if you look at, this is I, because I is taken as a reference in this context. I'm taking I as a reference because the series circuit. So this is VR, I into R. This is VC, I into XC. And this is VL. Okay? That is I into XL. Both will get cancelled, and finally you got I, and this is VR. Okay? And this is also V. Yes or no? Because V is equal to VR plus J VL minus VC. But VL VC got cancelled and V is equal to VR only. So therefore, the phasor diagram at resonance will become the total voltage is in phase with the total current. Understand all of you? Okay. So I, the current will be V by Z, but you know that at resonance, this part is what? 0. Therefore, this becomes V by R. I when omega is equal to omega R. Understand all of you? Okay. So VR will become V at resonance. Understand all of you? Okay. So this is very, very important here. And please note down, I will discuss important characteristics. Okay. Note down. Note down quickly. I just come back in a minute. Hope you have noted down. Okay. So important characteristics. Important characteristics. The first one is impedance versus omega. I mean frequency. The second one is current versus frequency. Keeping in mind that voltage, okay, voltage is constant, the magnitude is constant. Third one is the phase angle versus omega. So these are the important characteristics. Now let us discuss one after other, okay. The first one, I start with what? Z versus omega, impedance versus omega. We know that impedance is root R square plus, okay, XL minus XC whole square. Yes or no, all of you? Okay. When the frequency is 0, you know that XL is 0, right? And XC is infinity. That means what? X is much more greater than what? Higher than what? XL. And this is infinity. Understand all of that? That means the total circuit is behaving like what? A pure capacitive. So when omega is 0, the circuit is behaving like what? Capacitive. Yes or no, all of you? It is behaving like what? Capacitive. So then impedance becomes what? Impedance becomes what? 0. Sorry. Infinity, right? So if you substitute here infinity, you also get what? Infinity. Understand all of you? Okay. So what will happen here? It is behaving like what? Capacitive circuit. Behaving like what? Capacitive circuit. Now omega is equal to infinity. Then XL is infinity. Then XC is 0. Then Z becomes infinity. Again it becomes infinity because XL is infinity this time. Now this is behaving like what? Inductive circuit. Yes or no? Inductive circuit or lagging power factor circuit. When omega is 0, omega is equal to omega R. Already omega is equal to 0 we have seen. Then omega is equal to infinity we have seen. Suppose at resonant frequency when you see here, then XL is equal to what? XC. Then Z becomes what? R. That means it becomes what? It behaves like what? Resistive circuit or else a unity power factor circuit. Clear all of you? Now let us see the individual characteristics. Even we also see Z versus frequency, XL versus frequency, XC versus frequency, R versus frequency. Clear? So let me take this off for a moment. Let us see the characteristics, okay? Now if you see the characteristics, look at this all of you. Omega, right? This is what R, because R is independent of frequency. Agree all of you? R is independent of frequency. JXL in the first quadrant minus JXC in the fourth quadrant. Yes or no, all of you? In the complex plane if you see. Jxl is in first quadrant, minus Jxc is in fourth quadrant. Understand all of you? So this is inductive, this is capacitive. As far as XL, XC or impedance is concerned. So Z, XL and XC. Understand all of you? Okay. So now when you take here a line passing through the origin, because XL is directly proportional to what? XL is equal to omega L. XC is equal to 1 by omega C. XL is directly proportional to L. Understand all of you? Okay. So let me draw clearly here. Okay. XC, similarly, when you take XC, okay, let me take some measurement here. XC is inverse hyperbolic because X is inversely proportional. Yes or no? So when you take here, okay, this is what actually XC. So this is XL, this is XC. Now this is a frequency at which XL is equal to XC. When XL is equal to XC, what is the Z value? This is the Z value. But initially, what is the Z value here? Z value when frequency is 0 is infinity. When frequency is infinity, then also it is infinity. But when frequency is resonant frequency, that is omega R, okay, when omega is equal to omega R, at this point, the frequency, the Z value becomes what? Only R. That means it starts somewhere and reaches 0, R, and then again it increases. So therefore, it's something like this. Understand all of you? Okay. So this is what Z minimum. What do you call it? Z minimum. Understand all of you? Okay. So this is a minimum impedance point. So when do you get the Z minimum in RLC series circuit? When omega is equal to omega R. Understand all of you? Okay. So impedance starts from infinity and then comes down, okay, and becomes minimum and then increases. Getting all of you? Okay. So these are the characteristics. You can see here you can see this is capacitive. This region is capacitive. Okay, it behaves like capacitive circuit or leading power factor circuit. What about this? From resonant frequency, it behaves like what? Inductive circuit. And at this frequency, it behaves like what? Resistive circuit. Very important because 1 mark questions are coming in the exam based on these characteristics also. Understand all of you? Okay. So please note down quickly. Note down quickly. The characteristics are very, very important. Right. Right. Okay. Draw them carefully. This is impedance. Impedance versus frequency, XL versus frequency, R versus frequency, XC versus frequency. At every frequency, the Z value is R square plus XL minus XC whole square. Understand? So what will happen when omega is equal to omega R, XL and XC both will get cancelled and Z remains what? Only R. So Z becomes R. This is the lowest value because it starts from infinity and reaches minimum. Then again it goes to infinity as the frequency increases. Okay, as the frequency increases, Z decreases, reaches to minimum, then again it starts increasing from resonant frequency. Okay, right. Note down that. Hope you have finished this part. Okay, please draw them. I meanwhile just remove this part. Okay. Okay. Another important point to be noted in the exam point of it's very, very important. He asked the question one time in the gate examination. Okay. So note, if R is equal to 0, okay, then what will happen here? When omega is 0, then Z is what? Infinity. Then Y is what? 0. And the circuit is behaving like what? Capacitive. Yes or no? When omega is equal to infinity, Z is what? Infinity. Still Y is 0 and is behaving like what? Inductive. When omega is equal to omega R, Z becomes what? Because R is 0. Actually Z is equal to R, but R is 0. 0. Then Y becomes what? Infinity and behaves like what? Resistive circuit. Is it clear all of you? Well, now look at this. As far as admittance is concerned, when you know impedance, you can also find admittance here, but for this condition. Getting all of you? For this condition. You also know that when there is Z minimum, then obviously Y becomes what? Maximum. That is what happened here. Z is minimum, but Y is maximum. Z is maximum, but Y is minimum because they are reciprocals, right? Y is a reciprocal of Z or Z is a reciprocal of Y. Now, if you draw the characteristic, it's very, very important. In the exam, it was asked actually, okay? He was asking the Y versus omega. If the frequency of resonance is omega R, this is a line because at all these, the frequency value is how much? Omega R only, right? At this point, at this point, at this point, or whatever it is, right? Now, I would like to draw Y, how it varies. I would like to know, okay? The Y value, if you see, the Y value, if you see, it starts from 0, okay, and reaches to 0. It starts from 0, 0 to what? Infinity, then infinity to 0. Yes or no? Omega equal to 0, then omega is equal to omega, then omega is equal to infinity. That means when omega value varies from 0 to omega R to infinity, then Y value changes from 0 to infinity to 0. Yes or no? 0 to infinity to 0. Yes or no, all of you? Okay. So it starts from 0. And secondly, at this point, it is what? Capacitive. First, it is capacitive. So admittance, capacitive, admittance it is. What do you mean by admittance? Actually, you know very well. Yes or no, all of you? The location of this admittance, the impedance when it is capacitive, it is in fourth quadrant. But admittance is in first quadrant. Agree all of you? Impedance inductive, it is in first quadrant. But admittance inductive will be in fourth quadrant. Yes or no, all of you? Okay? Because admittance for capacitive, it is A plus JB form, G plus JB form. But impedance, it is R minus JXC form. Therefore, admittance for capacitive, it is in first quadrant. Admittance for inductive, it is in fourth quadrant. Understand all of you? Okay. Therefore, now it is something like this. It starts from 0. Okay. It starts from what? 0 and reaches what? Infinity. Getting all of you? Reaches what? Infinity. It reaches infinity. It reaches infinity. Then from infinity to 0. Understand? This infinity or that infinity both are same. Yes or no, all of you? At resonant frequency, okay, at resonant frequency, omega is equal to omega R. It has reached admittance infinity, but from infinity, from infinity, for any value of that omega increased, even a small omega also increased here, or increased by a smaller value, then immediately from capacitive to inductive, it will be entered, and finally it reaches to what? 0. So from capacitive, It reaches, it is already in capacitive, and all of a sudden it will enter into what? Inductive. Further, if you increase omega beyond the omega r, understand? Okay, beyond omega r, because it is now resistive. It is now resistive at this omega r. Then from omega r, if you increase, then what will happen? It will enter into what? Inductive. Now tell me, for admittance, inductive, where is it located? Tell me, all of you. Where is it located? It is in fourth quadrant. Therefore, it starts something like, you understand? Okay. It's something like this. Let me draw it again. Okay. Let me draw it again. That's it. Clear? Okay. So very, very important, because one mark questions are coming in a different way, because giving 4 characteristics, A, B, C, D options. In that, one option will be like this only. So this is what actually what? Capacitive. What about this? Inductive. I hope you understand. Admittance capacitive is in first quadrant. Admittance inductive is in fourth quadrant. We already learned all these things in our AC circuits. So all those concepts will help you a lot. Understand all of you? Okay, whatever we discuss, RLC circuits, the phasor diagrams, the triangles, impedance triangle, admittance triangle, power triangle, everything we discussed, right? So please note down that. Second important characteristics. So this is very, very important concept I'm telling you in gate point of view. Okay, there is direct question on these characteristics. Now current versus frequency. You already know that I is equal to V by Z. I is inversely proportional to Z. Then obviously you get the characteristics. Okay, this is I, and this is what the point where it has reached maximum value. This is called I max. .707 times of I max. You call it 3 dB line. You also call it what? 3 dB line by root 2, or 0.707 times of I max. Both are same, right? This is the frequency at which resonance occurs, where you find I max. Z min, but I max. Okay. This is what the frequency, half power frequency, another half power frequency. There is a frequency omega 1, lower half power frequency, upper half power frequency, or 2 cutoff frequencies, you can say. The difference between these two is called bandwidth. Understand all of you? Okay. The difference between these two frequencies is called bandwidth. Clear? Please draw them. Draw them. Current versus frequency. Understand? That is current versus frequency. Current versus frequency. Now this is what actually happening in the communication systems. A signal transmitted by the transmission station and received by the receiver is based on a resonance phenomenon, we said, because resonance circuit is a frequency selective circuit. Now the receiver will receive the signal in this range. Okay, so the bandwidth now, bandwidth is nothing but what a small range of frequencies. Okay, small range of frequencies. The signal transmitted by the transmission station in this range of frequencies, now that same signal is received by the receiver. Understand all of you? Okay. Now the bandwidth, now is it supposed to be the higher value or lower value? Yes, tell me all of you. The bandwidth is supposed to be higher value or lower value? It should be as higher as possible or as lower as possible. As far as communication systems are concerned, okay, as far as communication systems are concerned, the bandwidth must be as lower as possible. Understand all of you? Okay, the bandwidth of the the circuit must be what? As lower as possible. Getting all of you? I'll come back to that point again. First, let us try to derive what is omega 1 and omega 2 here. So at P1, this is a half power point. You call it P1, P2 are half power points. Okay, they are called half power points. Why they are called half power points? Because I max by root 2. Power is nothing but whole square. Yes or no? When you take square, the root 2 square becomes 2. So by 2 it is becoming. So the power is becoming half. Current is 1 by root 2 times, but the power is half times. That is why the point is called half power point. At P1, let us say omega is equal to omega 1. And we know that it is acting like what? Capacitive circuit. Yes or no? Therefore, the impedance is nothing but root r square plus 1 by omega 1c, xc minus xl square. Yes or no? Omega 1 L whole square is equal to voltage V by, what is that actually? The value of current here, I max by root 2. But you also know that V by I max is nothing but what? V by I max. What is I max? It is a current at resonant frequency. The current at resonant frequency, if you see, it is the impedance. The impedance at resonant frequency is how much? V by I max is nothing but Z. But at resonant frequency, Z value is what? Actually only R. So therefore, it is root 2 times R. Okay, you call it equation 1. From this, I can simplify it. Because I know that R square plus 1 by omega 1c minus omega 1 L whole square is equal to, when you take square on both sides, what do you get, Nana? When you take square on both sides, what do you get? This is 2r square. So you know that r square will get cancelled. And finally, when you simplify this, what do you get here? Omega 1 square. Yes or no, all of you? L into C. Omega 1c into, okay, into 2. Getting all of you? So finally, you're getting what a quadratic equation. And if you solve this, I'm sure that omega 1 is equal to minus r by 2l plus root r by 2l whole square plus 1 by LC. This is half power frequency at point P1. Getting? Now similarly at P2. What is omega? Omega is omega 2. And the circuit is behaving like what? Inductive circuit. Is behaving like what? Inductive circuit. So finally you get, you get now Z is equal to root R square plus omega 2L minus 1 by omega 2C. Because it is inductive, let us take XL minus XC. But what is the frequency? Omega 2. It is again V by, what is the current flowing here at this point? Also the same current I max by root 2. Okay. V by I max is how much actually? Z. But what is Z at resonant frequency? It is R only. So therefore, it becomes again, root 2 times R. This is again second one. Again take square on both sides. You will get r square plus omega 2L minus 1 by omega 2C whole square is equal to 2r square. Okay, r square and r square will get cancelled here. Understand all of you? Okay, 2r square and 2r square here, r square. You'll get 1r square. So therefore, what do you get? Again, square will get cancelled, and you simplify it. I'm sure that you'll get it. Okay, you can easily do that. It's not a complicated derivation. It is very simple one. I'm directly giving that expression. Okay, but derivation is also very important, my dear students, because sometimes he's asking the question based on this relation. Sometimes he will give you at what frequency the current through the circuit becomes 0.5 times of Imax. In that case, again, you are supposed to solve the problem like this only. There was one problem in gate asked actually. Here we are taking the current at this point is what Imax by root 2. Sometimes he will give you at this point the current is, okay, or at another point on this particular current, the waveform, okay, the current diagram, he will give you 0.5 times of Imax or half of Imax. So at what frequency it comes? You have to find that frequency. So how do you do that then? The root r square plus, okay, he will mention whether it is inductor or capacitor, will clearly understand that fact from the data given. Okay, now you will proceed accordingly, whether it is inductor or capacitor. If it is capacitor, use this formula. If it is inductor, use this formula. Then is equal to V by Imax by 2. Now it becomes 2 into R. Understand? Then again you have to derive it. So you have to follow the same procedure. Sometimes he is asking the questions in a different manner. But the derivation is very important to solve such kind of problems. But the formula you can remember here, omega 2 is R by 2L. R by 2L. Okay. Plus root R by 2L whole square plus 1 by LC. It's very, very important. Clear all of you? Okay. So please note down. And okay, before you note down, let me write even what is the bandwidth. Bandwidth is omega 2 minus omega 1. Okay. What is bandwidth? Bandwidth is omega 2 minus omega 1. So if you do that, it becomes what? R by L. Yes or no, all of you? Okay. Because both will get cancelled. R by 2L plus R by 2L. Finally, you get what? R by L. So bandwidth is R by L. You can see the bandwidth is directly proportional to R, or bandwidth is inversely proportional to L, and bandwidth is independent of C. Yes, sometimes he's asking 1 mark questions on this particular relation also. Independent of capacitance C. Okay. If capacitance value is doubled, then what will happen to the bandwidth? He's asking the questions in 1 mark questions, okay, in many of the competitive exams, okay. So please note down this, the bandwidth, omega 2 minus omega 1, R by L. So please note down this quickly. Quickly note down. This part. So students, you can see now, I think from this we understand the bandwidth part, which should be higher or lower. So as I told you, the bandwidth in communication systems, please put a note and write down first point. In communication systems, the bandwidth must be as smaller as possible. Because selectivity of the circuit, resonant circuit, is inversely proportional to the bandwidth. The reason is what? Selectivity is inversely proportional to bandwidth. What do you mean by selectivity? We said it is a resonant circuit is also called frequency selective circuit. The ability of the resonant circuit to respond to the particular frequency or small range of frequencies should be very high. Okay, the ability of the resonant circuit to respond to a particular frequency or small range of frequencies and rejecting all other remaining frequencies. That ability should be very high. If that ability is to be high, then bandwidth must be smaller. If it is larger, then it is inviting all frequencies. Then the resonant circuit doesn't understand which frequency is supposed to be picked up. So the ability to respond should be very high. So if it is to be high, that is called selectivity. The selectivity is high only when bandwidth is low. But in control systems, very, very important point, bandwidth must be as larger as possible. As larger as possible. Reason is, the rise time is inversely proportional to bandwidth. Understand all of you? The rise time is inversely proportional to bandwidth. I hope you understand the point. Rise time. What is the rise time actually of any control system? How you define? It's the time taken for the response to reach 100% of the final value in the first attempt. That means the response must be very faster. Once you give an input, the response must be faster. Otherwise, the system is called sluggish or lazy. Yes or no? So the system must be always faster in the response when the input is given. So in such case, the rise time must be very small. Okay, the rise time must be very, very small. So the rise time should be low. Okay, it is possible only when bandwidth is very high. Understand all of it? The selectivity is high only when bandwidth is lower. The rise time is lower only when bandwidth is higher, because the relations are very important, especially in interviews. I'm telling you, okay, selectivity is inversely proportional to bandwidth. That is why the bandwidth must be lower in communication systems. In control systems, the bandwidth must be larger because the rise time is supposed to be smaller. Understand all of you? Okay, so this is very, very important in the interview point of view. Okay, so we'll come back again in the next session discussing about what is selectivity and what is the quality factor and all those things. Will important discussion we have. We'll do that in the next session. I stop the session here.